Well, hello there, physics students. So, yesterday I tried to work from home. Day before, I packed up lots of stuff out of my room, went home, trying to make it work. And today I find myself back here because the technology just isn't the same. I know that some of you are having some issues, I think, with the videos. Hopefully, watching over YouTube, I think the YouTube videos are usually compressed enough that, from what I understand, most of you are able to get at them. Making the videos and uploading them has been a different story. So here I can upload a 20-minute video in 2 or 3 minutes. At home, that might be an hour, and then I get to the end of the hour of waiting, and it doesn't always work. So I'm back at school for doing this. I got to show you something. I took all my equipment home, which means I took my tripod and camera mount and stuff home, and I forgot to bring it back with me today. So get a load of my camera stand. I got a nice library cart, a couple of books, our dynamics cart from our Newton Second Law lab with the block taped to the top, and then I got my photo gate, and it seems like I can put my phone right on in here, and voila, we have a camera stand. Just don't bump it. Now I say that, and just watch, it'll probably fall over halfway through the video, and my camera will bounce off, hit the floor, break, and then what am I going to do? I don't know, but let's knock on wood. So alright, here we are, Physics, Thursday, March 26th. Learning targets. I can recognize the proportional relationships that exist between force, mass, and acceleration. I can perform simple calculations involving Newton's second law. I can define friction and describe some common characteristics of friction. And I can perform calculations involving friction. So I haven't really thrown out much new content to you in a couple of days. So here we're getting into a few things, and we're going to practice some exercises. All right, this is from your Newton Second Law lab. Okay, I truly hope that you have a chart that looks something like this for part 1. Okay. And it really worked out, the lab worked out quite nice. Here's my acceleration versus mass. So mass was the thing that we controlled from one trial to the next. That's the thing that I adjusted, and then as a result I measured the acceleration. So what you adjust in an experiment is called the independent variable. Independent variable goes on the horizontal. The thing that changed as a result is called the dependent variable that goes on the vertical. And when we graph this out, you see this? I very much like the fact that we have that shape. And I want you to think to yourself, what is that shape called? If you said hyperbola, good news. Okay? And then ask yourself, what does that shape signify? If you said inverse proportion, good news. Okay? So we just learned that acceleration and mass are inversely proportional to each other. So inversely proportional means if you multiply them together, acceleration times mass equals some sort of constant. I was just going to put a C for constant here, and I got ahead of myself. So, well, what did we hold constant in this case? Well, we had force. Now we're more used to seeing this as F equals ma. That's Newton's second law. When we look at the next graph, this is the data from part 2. Again, what I changed in the lab was the force on the end of the string. So because I changed that, that's my dependent variable. What changed as a result was the acceleration, so there's my independent variable. That's why I chose these axes. When we graph it, what I notice is that's not what I wanted to do. That's supposed to be a straight line. It's very linear. And linear, okay, I didn't give you a chance to try to think of that name. But when we see a linear graph, what type of relationship are we thinking about? Think about it a few seconds. We've got a direct proportion. We've got a direct proportion between acceleration and force. So a direct proportion is when the ratio is constant. Now, the ratio A over F equals M? Well, turns out that's not quite right. If we take acceleration, let's see, acceleration is going to have labels of meters per second squared. And if we put that over the force, which is in newtons, but a newton is a kilogram times a meter per second squared. We look and we see that, hey, we got meters per second squared on top and on the bottom. So our answer is 1 over mass. Oh, okay. This is 1 over mass. So if I flip that over, force over acceleration equals mass. If I multiply both sides by A, I would have F equals ma. Oh, same thing that I got before. The fact that this graph is showing us a direct proportion and this graph is showing us an inverse proportion leads to this formula. Okay? So proportionalities. Mass times acceleration is a constant, and acceleration over force is a constant. So therefore I can say force over acceleration is a constant. And when you combine it all together, turns out we got the same, we're all talking about the same issue. We end up with F equals ma. That is our relationship for Newton's second law. These two are inversely proportional. Force and mass will be directly proportional. Force and acceleration are directly proportional. So, let's do a couple of basic problems. What force is necessary to accelerate a 5.45 kilogram ball at 3.33 meters per second squared? Well, force equals mass times acceleration. Folks, if you haven't done it yet, always start out with a formula. Write it down. When you just start writing numbers down and then on top of it, some of you don't even put labels on your numbers, it's pretty meaningless. So this is telling me what I'm doing. Now I'm looking at, well, my mass was 5.45 kilograms, and my acceleration was 3.33 meters per second squared. A kilogram times a meter per second squared is a Newton. And all I have to do is take 5.45 times 3.33. And, that's a little over 5, a little over 3. 5 times 3 is 15. So I'm expecting an answer, 17, 18, somewhere in that range. Okay? How many sig figs can we have? Well, we got 3 there and 3 there, so we'd round our answer to 3 sig figs. And I guess I should grab a calculator so I can finish this. I was going to reach into my pocket and grab my phone, but my phone is where you are. Alright, so I got 18.1 newtons. Always nice to have a little box or circle or something around your answer. That's as basic as a second law problem gets. Okay, straightforward. Had the formula, didn't have to rearrange it or anything, didn't have to deal with any special labels. Multiply them together, got an answer. You need to get across to yourself that a kilogram times a meter per second squared is a newton. Another example. What is the acceleration of a 1,250 kilogram car when a net force of 6,350 newtons is applied? So, I'd like you to figure out what's our formula, what are we trying to calculate. If you have to, rearrange your formula for that. Pause until you have that done. I'm hoping that you paused and did that part. If F equals ma, and we're looking for acceleration, A equals F over m. Okay? Now go ahead, plug in your numbers, look at your labels, try to calculate your answer. Pause the video until you have that done. I'm hoping you did it. 6,350 newtons on top divided by 1,250 kilograms on the bottom. Now here's where you look at your labels and say, hey, I know the definition of a newton. A newton is a kilogram times a meter per second squared. So if I do that, now I can recognize that kilograms cross off, and I'm left with meters per second squared. The rest of this is a division problem. 6,350 divided by 1,250, 5.08. Box or circle around your answer. Another pretty straightforward problem. Example 3. If a net force of 475 newtons causes an acceleration of 12.7 meters per second squared, what is the mass of the object that's being accelerated? I'd like you to work out a formula. Pause until you have that. Hope you did it. If F equals m times a, in this case, we're looking for the mass, so mass equals F over a. Plug in your measurements and do your math. Pause until you have it done. Hope you have it done. Alright, our force was 475 newtons. And we're dividing by an acceleration of 12.7 meters per second squared. I know that a newton is a kilogram times a meter per second squared. So therefore, I can cross off the meters per second squared, and I'm left with just kilograms. Good news, because I'm looking for our mass. I hope I'm in kilograms. And we take another division problem. 475 divided by 12.7. All right, 37.4. Okay. So, a couple of basic second law problems. You see by the looks of these, they're pretty simple. The only way to really complicate this part would be as if maybe I gave you some weird labels or something, and you'd have to do a unit conversion. By itself, the Newton's second law problems are real simple. We've got to learn how to apply Newton's second law into other types of problems. that leads us to our next topic. So we're going to talk about friction. All right, what is friction? Friction refers to any force that opposes motion. So if I have a hand and I'm trying to move it, but this other hand it's kind of sticking to, there's friction between. There's resistance to moving. There's friction between my feet and the floor. There's a friction keeping your shoelaces tied. If you're holding something in your hand, there's friction keeping it in your hand. It opposes motion. So oppose means to work against. So what friction always tries to do, if you have something that's moving, friction is trying to slow you down. If you have something that's trying to start moving, friction holds it in place. So I happen to have this protractor just laying on my desk. And if I start tilting my hand, you see it doesn't immediately slide off my hand. There's friction keeping it from moving. Now, as I tilt my hand, eventually the friction's not going to be enough to overcome the weight and it slides off. There's friction is opposing the motion. What does friction depend on? Well, it depends on the materials. Okay? Think about walking across the floor with different foot coverings. Okay? If I'm wearing tennis shoes, or well, not tennis shoes, but court shoes, basketball shoes, on a wooden basketball floor, there's a certain amount of friction. If I want to go out dancing, well, not that I do this, but if you watch the videos, some of you like that country music stuff. You want to go out line dancing. Well, there you want a nice leather-soled shoe or something where it moves a little bit, but not too much. Maybe you've got a dog, and maybe you've got hardwood floors, and maybe you have at some point tried to play fetch with your dog in the house, and you throw the tennis ball, and the dog chases the tennis ball, but the dog's feet on hardwood floors doesn't have a whole lot of friction. So friction depends on the nature of the materials. It depends on both materials. So I have different floor surfaces, and I have different shoe surfaces. If I'm running in track and field and wearing spikes, so I get maximum friction trying to grab onto that, grab onto the track. If I'm skiing, well, I don't want friction on the bottom of the skis. I want those to glide nice and easy. But if I turn the ski sideways, I want the edge of the ski to grab hold of the snow. So, difference in nature of materials. So what does it depend on? Friction depends on the force of contact. So if I've got my hands and I'm trying to slide one hand past another, that's pretty easy. But if I push my hands closer together or tighter together and then try to go sideways, there's more friction holding it together. And, I noticed the heat build up right away too. So friction is a dissipative force. It changes the energy of motion into other forms of energy. Perpendicular force of contact, it's called the normal force. All right, so if another property of friction is friction acts parallel to the surface. So here's a block on a surface. And if I apply a force to the block, pulling one way, so I use my symbol F sub APP for applied. F is force, there's my applied force. If I'm applying a force this way, the friction is trying to keep me from moving, and the friction is going that way, and the friction is always parallel to the surface. Here's a block that's on an inclined plane. So, what are the forces acting on it? Well, the weight is acting straight down. It can't move straight down. So what we do is we break the weight up into two components. Remember components? One of those components is perpendicular to the incline, and one of those components is parallel to the incline. The parallel component is trying to make the block move down the ramp. Now, picture this. If the ramp gets steeper, the parallel component gets bigger, right? That's why when I held that protractor on my hand and I tilted it further and further, it eventually got to where the parallel component was more than the friction, and then it accelerated. Up to that point, friction held it in place. So if I want to know my friction in this case, the friction is in the opposite direction of my parallel component, because my parallel component is the part that's trying to make it move this way. Friction is opposing and friction is parallel to the incline. This guy up here, F sub n, that's my normal force. That's just the incline is pushing back because the block isn't going into the incline. The perpendicular component is balanced by the normal force. So imagine I got a block on a table and I take a magnifying glass and I zoom in and I see that the block and the table aren't perfectly smooth. There's little grooves and ridges and dips and divots. And let's say I look even further in there. I get down to the molecular level and I see that there's maybe intermolecular attractions between the surface. Some molecules are attracted to other molecules. So some of the causes of friction include the roughness of the surface. You know, if I've got my fingers kind of settling together and they're settling into grooves, and then I try to move my hand sideways, they have to plow across those ridges. So the roughness of the surface, but also intermolecular forces. Picture tape. You put a piece of tape. I have myself been taped to the wall in the school once. Stood me on a chair, put a whole bunch of duct tape on me, pulled the chair out, I was hanging on the wall. That took a lot of tape, a lot of surface area, but you think, what is it really doing? Gravity's trying to pull me down. There's a force opposing that, which is friction between the tape and the wall. Well, in that case, the friction is almost entirely due to the intermolecular forces because the adhesives are attracted to the wall. Friction, the amount of friction is proportional to the normal force. So the harder you push things together, the more the contact force, the more the friction will be. And there is something called the coefficient of friction. It's given the little symbol mu. Yeah, that's the same mu that we used for micro in the metric system. The coefficient of friction is the ratio of the frictional force to the normal force. Okay? Students misunderstand this sometimes. Mu is not the amount of friction. It's basically a property of a surface. If you go into law enforcement, and there are people in law enforcement who are trained in crash scene investigation, and what they might do is they might look at, all right, what's the condition of the tires, what was the condition of the road, what was the weather conditions this night, and they know from those conditions they can look up what the coefficient of friction should have been, and you combine that along with the measurement of skid marks and stuff, they can get ideas for how fast vehicles were moving and all sorts of things. So this is the frictional force. This is that ratio that describes the surface. Okay? But the bigger the normal force, the bigger the frictional force. These two are directly proportional to each other. Sliding friction is less than static friction. Sliding friction is also called kinetic friction. It's moving. So if my hand is moving across the other hand, they're touching each other. There's a resistance to the motion, but it's still moving. If my hands are stopped, the friction between the surfaces is actually a little bit more than once they start moving. Picture this. You've got a great big box on the floor that you're supposed to move. And the box is too heavy for you to lift, so you try to push it. And you got to get a big heave going to try to get it moving. But once it starts moving, it's a little bit easier to keep it moving. If you've ever had to push a car, it's hard to get it started moving, But once it starts moving, it's a little bit easier to keep it moving. If you've been driving in a car on icy roads, our wheels are supposed to come down and grip the road. We want static friction. Static is not moving. We don't want the wheel sliding across the road. If you've experienced it, when the wheel starts to slide across the road, now you really have trouble controlling your car, and the friction becomes less. Sliding friction is always less than static friction. Sliding friction can be called kinetic friction, moving. Static friction is sometimes called starting friction, because it hasn't started to move. We'll work a couple examples. I know the video is getting a little bit long. We'll work a couple examples and then you'll have some practice. So, if a force of 400.0 newtons is enough to make a 1,760 newton object move with constant velocity, what is the coefficient of friction? Now, there's some information there. We're going to need a free body diagram. So, I've got an object. I like to draw simple objects. There we go. That'll work. What do we know about the object? It has a weight. I'm going to call this FW. And the weight is 1,760 newtons. Okay, I know that, and I can infer it from the problem because it says a 1,760 newton object, and I know newton is a unit of force. Well, what force is an object like? Its weight. Okay? We're applying a force of 400 newtons to move with constant velocity. So which direction are we moving? You know, I didn't list everything in this problem, but I kind of think we're talking about moving it across a floor or something. So I know that my force this way, I really should draw that a little smaller because it's smaller than this force. I'm going to call this FAPP for force applied is 400.0 newtons. Yeah. We're looking for the coefficient of friction, so we want mu equals. Now, mu equals the force of friction over the normal force. That was our definition of mu. And I didn't tell you the force of friction or the normal force. So here's where your physics brain has to come in. Because this right here, constant velocity, that means something. If anything is moving at constant velocity, that means that the net force is zero. It's not accelerating. If there had any net force on it, it would be accelerating, not accelerating. So what that tells me is, like this block is not moving, it's not accelerating up or down. So if the weight's acting down this way, the normal force is acting upward, equal and opposite. I think the normal force is equal and opposite to the weight. Now, with force problems, just a little note on signs. We can typically work out force problems in terms of just magnitude without thinking about the signs. The sign is included in our direction that we draw it. So if you get confused on that as we go along, please ask. But just for right now, let's just try to follow through it. I'm talking about the magnitude of the normal force equals the magnitude of the weight. Now, what does the friction got to be? Well, we know the friction has to be in this direction. And the net force has to be zero. So the friction has to be the same as the applied force. And somebody might be saying, well, if there's no force, how is it moving? See, it's already moving. It would take a force to stop it. No force means it keeps doing what it was already doing. That's Newton's first law. So from this, I'm going to say that the frictional force must be equal to the applied force. And now this becomes really trivial, because over here I can say, well, the friction is the applied and the normal force is the weight, and I gave those to you. So mu is the applied force of 400.0 newtons over the weight of 1,760 newtons. What happens to the labels here? I got newtons on the top, newtons on the bottom. The coefficient of friction is a ratio. It has no label. That's weird. 400 divided by 1,760. How many sig figs can we have? This had 4, this has 3, so I can get 3. I've got 0.227. That is my coefficient of friction. Now, calculation is really trivial. We had to recognize some things from this problem. We have to recognize the significance of constant velocity. That's going to happen in a lot of our problems. Constant velocity means zero net force. Now, it's not going to be in all of our problems, so watch out if something is accelerating. Definition of coefficient of friction, understanding that friction is always opposite our motion. Normal force is the contact force. Right? You can hopefully go back through that as often as you need to. That was the same problem. Oops, there we go. Okay. This will be our last example for today. If the coefficient of friction is 0.30, so I'm going to just say mu equals 0.30. What force needs to be applied? So we're looking for applied force to a 1.35 kilogram textbook. That's a mass. To make it move across a desk with constant speed. That tells me that the net force is 0. So I'm going to draw my object. Draw my desk. Let's think about it. We've got, going down, we've got weight. We've got normal force. We've got applied force. We've got friction. Okay? So, I'm told the coefficient of friction. Now, remember, a formula, coefficient of friction is the frictional force over the normal force. And the normal force equals the weight. Here's where students sometimes make a mistake. I have seen it so many times that students will plug in 1.35 kilograms as a weight. It's not. It is not a weight. Kilogram is a unit of mass. It's not a force, it's a mass. So, how do we find a weight? Well, I've told you a couple times now that weight is m times g. So we've got 1.35 kilograms times 9.80 meters per second squared. I'm going to just calculate that real quick. 1.35 times 9.80 equals 13.2 newtons. Okay, so that's going to tell me my normal force, and I'm looking for the applied force, which is equal to my frictional force. So I'm going to come over here. Let's see if I can take that, and I'm just going to move that out of my way. I can rewrite this and say mu would be, because my frictional force is equal to my applied force, over my weight, and I'm looking for my applied force, so my applied force equals mu times the weight, and mu is 0.30, and my weight is 13.2 newtons. I'm only going to be allowed 2 sig figs on this. 0.30 times 13.2 equals, oh, look at that, 4.0 newtons. .96 rounds up to 4.0. So, another sample problem. What I'm going to do is give you a few problems to work on and ask you to practice a bit. If you don't have all the lab work done, please watch the videos and resources I've sent you and make sure that you're getting that stuff done. I think that wraps it up for today. Sorry it's so late on getting you your assignment, but we're all facing challenges here, so doing what I can. I'm really trying to get my stuff organized that I can try to get some grades in the book, and I guess I'm hopeful that I think I got the groundwork made that I can get some actual grades done and in the books today. I'll be in contact with you. If you have questions, let me know. Have a great day. Stay safe.